Greetings and welcome to really what is kind of part two of the standardized mean difference effect size. This time we're going to do it for the dependent t-test. So again, I'll just, I guess, put standardized mean difference. This time we're going to do it for dependent t-test. Okay, I guess let's start with design on this one just to refamiliarize ourselves that and generally speaking a dependent t-test is where you're taking an observation on say maybe one group of n equals 20 folks or so and you're measuring them and then you're giving them some treatment and then you're measuring them again. So this is your pre-test, this is your post-test, and you just want to know how did they change, how did that group change as a function of the treatment. So they served as their own controls and then you just measured the same group of people twice. And so again, I guess if you're kind of looking at this from terms of columns, you had each ith person, 1, 2, 3, dot, 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 and you had all of their kind of pre-scores, you had all of their post-test scores, and then you got their difference scores. Then here you can get a mean of all the different scores, and so on and so forth. Okay, so let's look at the calculation. And you'll see this is actually very controversial. You'll see it many different ways in many different textbooks. I'm not going to get into all the different ways. I'm just going to kind of highlight maybe one or two things for you. So again, we're using small d here because it's the standardized mean difference. And we're going to say the mean of the difference scores divided by, I'm just going to put a box down here, divided by something. Now you might also see this as the mean of the different scores, like I've kind of drawn it over here. They mean the same thing. Now, what can go in the box? You could put in the standard deviation for the pre. You could put in the standard deviation for the post-test. You could put in the standard deviation for the average of the pre and the post. This would actually be calculated S average, the variance of the pre plus the variance of the post divided by 2 and take the square root of that would give you the average standard deviation. This actually might be the preferred way of doing it. I'll kind of just say that. I'm not going to show you this way because most textbooks actually don't have it. You'll see this method in journal articles, but in the textbooks you'll actually see probably this other way, which is what we call the standard deviation of the difference scores, which would be S diff equals the sum, and this will look like a familiar formula to you, the raw difference score minus the mean of the difference score squared divided by n minus 1 and take the square root of this. This looks very similar to our variance. If you remember, I'll do this in blue, where to get the standard deviation you take the sum of the x minus x bars squared divided by n minus 1. So very similar. Anyways, this is the one that we'll use. So suppose you had the following data, and I won't calculate all this out. Suppose you have the following data, where now you have the x bar of the pre equals, let's just say 103 again, and the x bar of the post equals 100. standard deviation of the pre equals 5.5, standard deviation of the post 4.5. It's the same data that we used from before. I'm going to throw in a new data point. We're not going to calculate it, but just say that this S diff right here was already calculated for us, and it was 7.1. So now we have everything we need for this. We've got this value, and we have this value, which will just be the 103 minus 100. So let's just say that D here equals 3 divided by 7.1, which now equals 0.423. So that would be your effect size here, assuming that you had calculated this out and I gave you all the raw data points, which I did not. But recall here, and I want to build this piece in, recall that statistics which come from samples are estimates of parameters which come from the population. You don't know what these differences are and what these effects are in the population, and so you take a sample from the population, you calculate statistics, you find out if you could consider those sample means to be different and what their effect is, and then you want to infer those back to the population. That's the whole point of inferential statistics. So if you remember, just by way of example here, that an X bar was the point estimate for mu of the population, so the sample mean is the estimate of the population mean, that the sample variance S squared was the point estimate of the population variance sigma squared, and the sample standard deviation was the point estimate of sigma, which was the population standard deviation. And the same is true for D. It estimates delta, which is this is the Greek lowercase delta in the population. So let's make the connection here. So kind of like this estimates this in the population, the effect size that we're calculating on our sample is an estimate of what the effect is going to be in the population. And just like if I put all of these individuals from which I got my sample mean back into the pot of beans and pulled out another sample from there, my mean would be just a little bit different. The same is true here for the effect size. If I calculate an effect size from that sample and then put all those individuals back into the pot and pulled out another group, I'd get a slightly different effect size. And so it's just one effect from a whole family of effect sizes. I'm not necessarily sure that that point is important for where we're at in this particular class, but I just thought I would kind of bring it up and at least introduce the concept. So this is the standardized mean difference calculation for the dependent t-test. Thanks for watching the video.